Okay, so we are discussing about virtual memory, and today we will complete this topic of virtual memory. So yesterday we discussed like two important algorithms which are used in a virtual memory system. One is a page replacement algorithm. The other is a frame allocation algorithm. So frame allocation algorithms decide things like how many frames will be allocated to a process, or even which frames can a process use, as in suppose a particular process PI has a page fault. Then a new page needs to be brought in the memory, and let's say there is no empty space in the memory, and no empty page or frame in the memory. So then will one page of PI itself be replaced, or is it possible that some other, page of some other process is replaced? Both are possible. There are trade-offs as always in systems, and both have been tried out, but usually people have preferred the global replacement policy where any page can get any frame in the memory. But again, that has its own disadvantages, as in, so the running time of a process may not be completely under its control. So depending on the system, all these considerations may change. Like if you have a real-time system, then maybe all these considerations will change, because then you can't say that, oh, a process took a bit longer time to handle a request because there was a page fault. In a real-time system, these kind of considerations cannot apply. Therefore, you have to think differently. Okay, so that was about page replacement and so on. So today we will discuss some other aspects of virtual memory. Let us start with an undesirable effect, which comes in due to frequent page replacement, and it's called thrashing. Okay, so what is thrashing? So the thrashing is the following situation. Suppose a process does not have enough of its pages in the memory. Then the page fault rate is very high. What does enough mean? We will soon discuss in detail, but just understand intuitively. That's in general, when a process runs, maybe it has a set of 10 pages, let's say, which it frequently accesses. Okay, maybe the different codes, the different data, a big array. So these are some of the things that the process frequently accesses. And let's say these require 10 pages. Now, what if one of those 10 pages are not in memory? Then there will be a page fault to get a page. So now one of the existing pages of the same process, let's say, is replaced for bringing in this new page. But then the process will quickly need the replaced page back, because as I said, this set of 10 pages, let's say, the process needs them frequently. So what happens? Say page 5 is not in the memory, so a page fault. So maybe page 7 is replaced with page 5, but then soon page 7 is needed. So maybe page 8 is now replaced with page 7. Again, soon page 8 is needed, and so on. So basically what happens is the process cannot get any useful work done. Rather, it is constantly busy swapping pages in and out. So this is about one process. Now think about it. Suppose multiple processes enter this kind of a bad cycle. So then that means the low CPU utilization. Why? Because CPU will be utilized mainly when the processes do some actual work. If the processes get busy swapping pages in and out, that means most of the work is being done by the memory management unit, DMA, and so on. So the CPU is not being utilized. Now, certain operating systems may work in this way, that it checks the CPU utilization. And if it finds that the CPU utilization is low, then it may think, the OS may think that it needs to increase the degree of multiprogramming. That means the OS is not understanding that the main problem is thrashing. It is feeling that there is not much computation going on because the CPU utilization is low. Therefore, let me bring more processes in the memory. So then other processes get added to the system, and this aggravates the whole situation. So basically this phenomena is called thrashing, where a process is not getting any useful work done, rather it is just busy swapping pages in and out. Okay. So this is a pictorial view of thrashing. So the x-axis is the degree of multiprogramming. That means the number of processes in the memory right now. And y-axis is CPU utilization. So in general, if you see, as the degree of multiprogramming increases, CPU utilization increases. And that is why we have gone towards multiprogramming, right? However, at some point, maybe you see a sharp dip. This is thrashing. because there are so many processes in memory now that maybe none of them are getting the full amount of memory that it needs to actually work. Clarification: we are not talking about virtual memory here. Virtual memory of every process is huge. That's fine. We are talking about actual physical memory frames. Maybe processes usually need 5 or 6 frames to work, or 5 or 6 pages to be in the memory. However, none of the processes are getting that. So basically processes are getting busy just swapping pages in and out. This is called thrashing. Now let's understand thrashing a bit. Or I made a remark earlier that enough, like a process should have enough pages, or thrashing occurs when a process does not have enough pages in memory. So what is that enough? Let us try to formalize that a bit. So think about it. Why does this whole, demand paging work? It works because of locality of reference. We know that if a page has been brought into memory, so if the CPU has started accessing a page, most probably that page will be accessed quite a few times in near future. That is why it makes sense to bring that page from disk to memory. So this is the whole idea of caching, with which you are all familiar. So essentially processes migrates from one locality to another, let's say from one function to another function. And at a certain point of time, maybe it needs certain parts of the code or data in order to work. So this is called a locality, right? So basically we need to allocate enough frames to a process to accommodate its current locality. Okay, current locality is roughly at this point of time, say this time plus say the near future, what are the pages that the process will need? Now it's not so easy to estimate the current locality, because the current locality can get defined by the program structure. So this slide shows two small snippets, code snippets. Okay, see, both of them are trying to access the same two-dimensional array A. Right? The difference is that in the left-hand side, every row is being accessed first. So it's a row major kind of, sorry, I should not, row major kind of accessing. So first row will be accessed, all elements of first row. Then all elements of second row will be accessed and so on. And in the right-hand side code snippet, it's opposite, as in it's a column major kind of addressing. So you see ij, but I is here the inner loop. So the right hand side code snippet we're working on, first all elements of the first column will be increased, then all elements of the second column will be increased and so on. Now think of a scenario that we have 512 byte pages and every element of array A is an integer of 4 bytes. That means what? 128 elements of array A fill a page. Now think that each row of the matrix is stored in one page. We know that is how arrays are stored in memory, right? In a row major format. So now you see the left-hand side snippet works on a per row basis. So then it needs one page at a time, because it will access the whole first row once. That means one page. Then it will access the whole second row, another page. So essentially it will need 128 pages. And again, if you think of a pure demand paging scenario, there will be 128 page faults. But think of the right hand side snippet. It accesses per column, and every element of a column is in a different page. So this is a very inefficient design. This will have 128 cross 128 page faults, because A11 is in one page, then it accesses A21. And that's in the second page. Then it accesses A31 in the third page and so on. Right? So basically the current locality may depend on how the program is written, and that's why it is not easy to estimate that. You cannot always assume that a program would be written very efficiently, etc., etc. So yeah, the current locality, it's not so easy to estimate. However, that is what people try to do. So let's see. Okay, so now that we understand what current locality is, let's say, so why does thrashing occur? It occurs when or if the size of locality across all processes. So the summation. So let's say there are k processes, P1, P2 up to k, and you compute the locality of each process and then you sum it up. So that is the minimum number of pages which, if you have in memory, all the processes can run for the next small amount of time, let's say. However, if this is more than the memory, then thrashing can occur, because there will be always some process or the other which will be suffering a page fault. Okay. So now let us understand how to. So see, we want to estimate the current locality, but we see it is not so easy because it might depend on program structure and so on. So let us see some way of approximating it. How do people actually try to estimate it? They use something called a working set model. So let's understand the model. First, delta is a working set window, which is a certain number of page references. Let's say all page references made in the last 10,000 instructions. The picture at the bottom of this slide shows a very small example. So again, see this sequence of numbers that you see, that is the page reference table. So that is the order in which pages are referenced, let's say. So think of the time T1. Let's say our delta is 2, 3, 4, 5, 6, 7, 8, 10 instructions. Our delta is 10 instructions. So what are the pages accessed in the last 10 instructions? That is the working set of process PI of this process. Now understand it changes with time. So at T1, let's say, in the 10 instructions before T1, the process accessed a lot of pages. So you know the working set is 5 pages, 1, 2, 5, 6, 7. But consider time T2. If you consider the 10 instructions before time T2, the process only accessed 2 pages, 3 and 4. Therefore, the working set is at 3 and 4. Right? So the working set of a process is the total number of pages referenced in the most recent delta. But delta, like in this small example, it's 10 instructions. Typically, you might think 1,000 or 10,000 instructions. Okay. Again, don't think 10,000 lines of code. We are talking about low-level instructions. Right. Okay, so is this clear? This is what is called a working set. Any doubts till now? So okay, just one thing is, yeah, what is delta? That is again a design choice. So you can see the trade-off here. If delta is too small, it will not encompass the entire locality. Like if I say delta is just 2 instructions, well, it will not encompass the entire locality. And if delta is too large, again the estimate will be overestimating the locality, right? Because it will encompass several localities. Maybe if you take 1 lakh instructions, maybe the code has gone through different functions during this delta. That delta is too large. Right, so yeah, what delta is, that is a system choice, a design choice, but in general, is the scheme clear? What is a working set? If any questions, please write. Okay, let me proceed if you have any questions, right? So this is the working set of a process, right? So now suppose we figure out the working set of all processes. See, what I have said is now not infeasible. Like measuring the current locality of the process accurately is difficult because it depends on the program structure, etc. But then what I said, if you consider the number of pages referenced during the last delta time or delta instructions, then that's feasible. So then you can figure out the working set of every process. So then you sum up, right? So you sum up the working set of every process in the system, and that is the total demand for frames across all PI. This is an approximation of locality. So if this sum becomes greater than the total number of frames that you have in the memory, minus, let's say, the frames that have been allocated to the kernel, then this may lead to thrashing. So a simple policy can be that the OS checks this at certain intervals of time, and if it finds that D is greater than M, then one of the processes have to be swapped out in order so that the other processes can run smoothly. So you want to avoid thrashing. So if this D greater than M, then we fear that thrashing may occur. Therefore, the OS might decide to swap out some process or something. Now the working set model is okay. I mean, it works. I won't say it doesn't work, but somehow, I mean, it's a bit indirect and so on. I mean, it requires a lot of computation, etc., etc. So then there is another scheme that has been proposed. It's called the page fault frequency. So it's a more direct approach than working set. So basically the system here has an acceptable page fault frequency. That means let's say that it's okay if 1 out of every 10,000 page accesses is a fault. I mean, anything more than that won't be acceptable. But if it is 1 in 10,000 or 1 in 1,000, then it's okay. So this is the acceptable page fault frequency. Then a per process replacement policy can be designed. So see the graph. X-axis shows the number of frames allocated to a process, and y-axis shows the page fault rate. Now you have this upper bound and a lower bound. So between, if the page fault rate is between in these two, upper bound and lower bound, then we say it's okay. So in this picture, let's say at the beginning with small values of x, the page fault rate is quite high for this process. That means what? We have not yet given this page enough frames to satisfy its locality. So then we should give it more frames. At some later point of time, let's say the page fault rate decreases quite a bit below the lower bound. That means that now this program does not need that big a locality. Remember that locality changes with time. So again, if I go back to that example, just like this, at time t1, the process actually required a lot of memory because the working set was large. At time t2, the working set is small. Right. So you can understand, having coded many assignments, etc. over all these years, you understand that at some points our program will make a lot of function calls, handle big arrays and so on. But at other times, maybe it will do some small applications, some small computations. So the memory requirement won't be much. So if that is the case, so it's in the higher x axis here, higher values of x, then the page fault rate is lower than the lower bound. That means we have allocated more frames to this process than what it needs now. So then maybe kernel may decide to decrease the number of frames. Okay. So again, decrease number of frames means I don't think that the kernel will suddenly come and start removing pages from the memory. But yes, maybe if some other process now has a page fault, then the kernel will mark that pages of this process can be replaced because clearly it does not need as many frames as has been allocated now. Okay. So these are two approaches to counter thrashing. One is that working set model, and a more direct approach is this page fault frequency. So any questions about thrashing or these ways of handling thrashing? Otherwise, we begin some other small issues. Shubham is asking, why do we decrease number of frames? It will unnecessarily slow the program, right? No, that's the idea. The program does not need this much memory now. So possibly removing a page will not slow it. And more important than that, even if it slows the program, it is not unnecessary. The OS will not do anything unnecessarily. As I said, it's not that the OS will suddenly wake up and decide, oh, this process is taking too much memory, let's reduce frames. No. So OS does nothing unnecessarily. These things will be done if other processes are getting too much page fault. Yes, what Pankaj said. frames will be reduced from this process only if it can help other processes to speed up. So maybe this process does not need so many frames now, other processes need them. Therefore, the OS will take the decision. Again, understand most of the things that the OS does is kind of overhead. Therefore, kernel usually does nothing unnecessarily. Okay, any other question? So if everything is going on fine in the system, the kernel is very happy to take a back seat and let things go on. Okay, so let me proceed with some other issues. These are some. Pankaj is asking how frequently is PFF calculated by the kernel? Frankly, I don't know because that's completely a design choice. As in, yeah, I really don't have any idea. It may be that, yeah, when the OS comes, when the OS is scheduled, the processor, at some points it might, or it might, it might well be that it's on a demand basis, as in maybe the OS just keeps a track of the number of page faults it had in the last few epochs or last few seconds. And if it is more than a threshold, then maybe these things are calculated. But really, I don't think it would be I don't think it would be very frequent operation, and it might also be demand based, as in if there are too many page faults, then some module of the kernel checks this and so on. So the kernel maintains the history. As we said, how many processes are, and which process is taking how much time, etc. Maybe which process is accessing memory. This bookkeeping kernel is doing, but yeah, how frequently are these operations invoked? I am not sure. As I said, it might not be a periodic operation. It might be need based. Okay, let me move on to some other issues. These are simple issues which. Okay, Pankaj, please unmute yourself. I'm not understanding your question.
Sir, PFF is calculated only based on past history, like how many page faults this particular process had in past.
Yeah. Yes.
Then that will, if it is, suppose initially it is too high, then basically it will already have a lot of page faults occurring, which will be unnecessary.
Yeah, that is what the picture shows. If it is the case, so when a process starts, it's usually not known which pages it will access. Therefore, it's normal that there will be more page faults, and that is that. So that will be tracked, and that will help the OS to decide how many frames maybe to allocate to this process finally.
Okay, so initially, whenever a process starts, there is a little inefficiency in execution. Like we do a lot of swapping.
Good point. Just give me 5 minutes. I think you will get a slide which will partially answer your question.
Yes.
But yeah, in general, if you don't do anything special, then it is true, because like if you follow a pure demand paging scheme, then a process starting will have lots of page faults, because maybe a process just needs 6 pages to start working. So if you follow a pure demand paging scenario, then it will have at least 6 page faults. But then can something be done? Yes, that we will come to in that other issues thing. Okay, so let me move on. Yeah, some other issues. Again, I'm not going to give any answers here. I'm just pointing out some issues that has to be kept in mind by the kernel designers. So one question is, what should be the page size? Again, no answers in this slide, but then this slide just lists down some factors which should be taken into consideration. Like how much internal fragmentation is okay. It's like if you give big pages, then the internal fragmentation would be large. Then the page table size would be small. So we had discussed this a bit earlier, but basically page size will depend on all these factors that are shown here. Some of the things may not be in your control. Say TLB. TLB is mainly a hardware. So, a processor has been given to you, maybe you cannot say, oh, I want a larger TLB because it's inbuilt, right? So some of these are under your control, some of these are not under your control, but all these factors have to be considered. So one thing is true, that page size is always a power of 2, and usually in the range of say 4 KB to 4 MB. Or okay, is this 4 GB? Oh no, 4 MB. Yeah, usually it's between 4 KB to 4 MB, but sure, I mean, some systems which know that huge memories are required may go for larger, etc. And yes, as we go ahead, I mean, with time, usually page sizes have increased because, as I said, processors need more and more memory. Now mankind is writing programs which need more and more memory and so on. Okay. When I say mankind, the girls don't feel bad. You are also writing big programs, but yeah. Okay. So yeah, but again, so there is no answer here in this slide. So please don't ask the next question, what should be the good page size? But these are some factors which have to be kept in mind. Okay. Next is exactly the point which Pankaj was asking. That's why I wanted to move ahead. So it's understood that if you follow a pure demand paging scenario, when the process will start, there will be a lot of page faults. We don't want that because every page fault means a lot of overhead. There will be a system call, the kernel has to come in, it has to do several things and so on. So then can we do this? Pre-page all or some of the pages a process will need even before they are referenced. Right? So this is something which is done by some kernels during a process startup. Of course, there is a trade-off here also. This will reduce number of page faults, but if the kernel mistakenly brings pages which are not going to be used, then memory frames will be wasted. So basically the trade-off is captured in what is written in the lower part of this slide. Assume that S pages are pre-paged and alpha of these pages are used. I mean alpha fraction. Okay, alpha fraction of the pages are used. So basically S multiplied by alpha, these number of page faults you save by pre-paging S pages. Okay. And what is the cost? S into 1 minus alpha. This is the unnecessary amount of pages that you are bringing in. So then which is more? Is cost of saving S alpha page faults more, or cost of pre-paging S into 1 minus alpha unnecessary pages more? Again, this is a design choice. You have to decide. But yes, typically, I mean, what we showed in the next picture or the discussion that we had with Pankaj, usually processors will have a lot of page faults at startup, which is not a very ideal scenario. Therefore, sometimes pages are pre-paged. Again, which pages to pre-page is an important decision. So again, I'm not sure what exactly is done. Sometimes there can be some heuristics. Maybe the compiler can actually put in some code to mark which is the starting point of the code of a process. I mean, that has to be known, right? Because when a process starts, finally the OS has to set the program counter to the first instruction of the process. So that means in the executable, which is prepared by the compiler, this is already marked that where the process starts. So maybe though that page and the next page is brought or something like that. So again, we are not providing any answers here. We are just introducing you to some issues which designers have to think about. Okay. So by the way, this pre-paging also tells you that pure demand paging may not be a very common situation. Often these optimizations are done like pre-paging and so on to reduce the number of page faults. Okay, another issue is what is called TLB reach. What is TLB reach? The amount of memory accessible from the TLB. So remember that the TLB is essentially a cache, an associative cache, where we want to keep a small number of pages which are very frequently accessed. So basically, and if the good part is that if we get the frame number of a page from TLB, we don't have to access the page table. So we save on memory accesses. The question is how many how much memory can we access directly from the TLB without consulting the page table. So TLB reach is TLB size into page size. So how many entries in the TLB multiplied by page size? Now, ideally, the working set of each process should be stored in TLB. However, this is an idealistic scenario. It does not always happen. The TLB may not be large enough, etc. Also, you might say, oh, okay, so I want a large TLB reach. Fine, then let me increase the page size. TLB size may not be in your control. The TLB is the hardware part which is given to you in the processor. But you say, oh, okay, the kernel may say, let me increase the page size. That will increase TLB reach. But then again, there is a trade-off that this will lead to an increase in fragmentation also. So if you decide huge page sizes, internal fragmentation will be more. Okay. The last issue that we are discussing is IO interlock. So continuing here, there are some pages which are used by almost all processes, or some code which are used by almost all processes. Think of the pages that are used for copying a file from a device. All processes are possibly using this, or a large number of processes are using this. So they must be also somewhere in the memory. Now suppose a page replacement algorithm mistakenly chooses that page to replace. That's bad because very frequently that page will be used by different processes. So we should prevent that. For that, pages are sometimes locked into memory. This is called pinning of pages to memory or IO interlock, something like that. Right. So some important pages which we always want to remain in the memory, they have to be interlocked to memory. Even some TLB entries can be interlocked. Like we specifically want to access this page without having to access the page table. Therefore, some important pages can be even interlocked into the TLB. So again, see, all these are optimizations in order to reduce the number of page faults. So yesterday we had this discussion. There are two types of optimizations, at least there are more, but at least two, which we have considered. Optimizations to reduce the number of page faults and optimizations to reduce the page fault servicing time. These two are related, but not exactly the same. Okay, any questions? Otherwise, just a small part remains, which we'll go through. Any questions at this point? Again, please don't ask me what is the solution of these issues. There is no one solution. These are design choices, which many factors have to be considered, and then the kernel decides these. So any other question, clarification? Okay, in the interest of time, let me proceed because I have to leave a bit early today due to another meeting. Okay, the last very small part that we would like to discuss is allocating kernel memory. Now, see, the memory management is done by some modules of the kernel. Other modules of the kernel can also ask for memory. Okay. So as you know, the kernel has memory modules. So some module of the kernel is handling memory. Okay. Other modules of the kernel can also ask for memory. Will such requests be treated similar to requests from user processes asking for memory? Again, it's a design decision. Some OS may treat them the same. Right, okay, whether it's a kernel module requesting for memory or a user process requesting for memory, we will allocate one page of memory, etc. Some OS may think that way. However, some operating systems may decide to treat such a request differently from a user process asking for memory. And in such cases, memory may be allocated from a free memory pool different from the list of frames used for user processes. Now the question is, why such different treatment? The two reasons here. One is that, again, see, kernel knows that basically it should not take too many resources. Understand this, over this whole semester, we are trying to tell you this, that in a way, whatever kernel does is overhead, because ultimately the useful work is done by the processes which the users run. And kernel knows that. Like kernel does not have any ego that I am the most important guy around here. No. So kernel knows that it should use as less resources as possible, as less memory as possible, as less CPU time as possible, and so on. So when some module of the kernel itself requests from memory, it may not want to allocate a one whole page if the demand is much less than the page size. The kernel actually needs memory for different structures, different data structures of varying sizes. But every time some kernel module requests for a memory, some small amount of memory, one page is allocated, that might not be a good option. Okay. So that's why it may be treated differently, not through this normal paging system. Also, you may have heard of something called memory mapped IO in your Koha course, etc., etc. So actually, sometimes kernel memory needs to be contiguous. For example, some hardware devices may interact directly with physical memory, and they assume the memory to be contiguous. Okay. So again, I'm not going into details here, but for these reasons, it is possible that the kernel decides to allocate memory to its own modules differently from how memory access requests from user processes are handled. So let us very briefly discuss two approaches for allocating kernel memory. Okay, in the next 5 minutes, I'm not taking questions. Let me just complete this, but then I'll take questions if you have. So these two approaches we will just discuss very abstractly. So one is called a buddy system. A buddy system uses what is called a power of two allocator. Okay, let me give the example on the next slide that will make things clear. So here there is a physically contiguous chunk of say 256 KB, which the kernel will take memory from. Now let's say some module of the kernel requests for 21 KB. So then this 256 KB space would be split into two equal splits of 128 KB each. Then one of the 128 KBs would be split into two 64 KB chunks. One of the 64 KB chunks will be split into 32 KB chunks. And see that power of 2, which is closest to 21 and just less than and just slightly more than that is 32. Okay, so it's known that exactly 21 KB won't be allocated. At least some power of 2 would be allocated, and the closest one which satisfies 21 KB request is 32 KB. So this chunk is used to satisfy this request. So the advantage of this is that it can quickly coalesce unused chunks into a larger chunk. So now if this 32 KB is released later, it can quickly it can quickly coalesce this with the other free memory. However, the disadvantage is that there is fragmentation. As I said, this module requires 21 KB, but it is being given 32 KB. So there is some internal fragmentation. But then this is a big advantage. Therefore, sometimes buddy systems are used. Also, another alternative mechanism is called a slab allocator. So a slab allocator works on the following principle. It's kind of known what kind of data structures kernels will need. For example, kernels will have to store process descriptors, semaphores, file objects, and so on. So some terms, a slab is one or more physically contiguous pages, and cache consists of one or more slabs. Okay. Now the idea is here is it is kind of known that what kind of data structures the kernel will need to store. Therefore, reserve a single cache for each unique kernel data structure. So each cache is filled with objects that are instantiations of the data structure. For example, you might have a cache for process descriptors, a cache for semaphores, a cache for file objects. By the way, don't mistake this with the cache that you have studied in Koha. That was a hardware device. I mean, here we are not talking of that. This also uses the term cache according to the book, but basically this cache is just some memory. The idea here is that a user process can ask for many different types of memory. It's no way possible to predict that. The different user processes, what kind of, someone can store an array, someone can store a hash table, who knows what kind of data structures user processes will store. But in case of the kernel itself knows what kind of data structures it needs to store. Like say, it will need a lot of process descriptors. It will need a lot of semaphores. It will need a lot of file objects. So why not pre-allocate memory with many instances of these data structures? So the advantage is that when say let's say a new process descriptor is needed, just allocate one process descriptor. So basically when the caches are created in the memory, they are filled with objects marked as free. Let's say the cache for process descriptors has several process descriptors, but they are uninitialized, so they are free. When a new object for a kernel is needed, a free object is simply allocated and marked as used. So every time a new process comes in, a process descriptor is needed. So just one free process descriptor will have to be allocated. Of course, if the slab gets full, then empty slab has to be allocated. If no empty slabs, a new slab has to be allocated and so on. So the advantage of this over say the buddy system is that actually no fragmentation and very fast memory request satisfaction. Because it's usually known that what kind of data structures the kernel would use, therefore pre-allocate memory for those data structures so that their requests can be quickly satisfied. Okay, so yeah, so just to summarize this part, sometimes memory requests from within the kernel can be handled a bit differently than memory requests from user processes. And we have very briefly discussed two schemes like buddy system and slab allocation, which can be used for memory allocation to kernel modules. Okay, that is all that I have to discuss. And in fact, today we are completing the part on memory. So yeah, we started off with contiguous memory allocation, which was very simple. Then we understood the problems. Then we moved to segmentation, paging. But even at this point, we were thinking that the whole process needs to be in the memory during execution. And then we changed even that, and we discussed virtual memory, demand paging, and so on. Of course, there are costs associated, like thrashing and all. So, but there are optimizations also, like using TLB, reducing the page fault service time, reducing number of page faults. So all these things are there. Okay, so that ends my discussion on memory. Like if you have any questions for a couple of minutes, I can address them. Okay, then fine. So tomorrow we will start a new topic, which will be file systems. And that topic, which is actually the major last topic, as in, if you think of the large topics which we are discussing in this operating system course, like say process synchronization, initially it was processes, life cycle of a process and so on, then process synchronization, etc. So we've spent several classes on memory. So one big topic remains, which is the file system, which will be started today. And that topic will be taught by Professor Mainak Mondal. Right, so that will start tomorrow. Okay, fine. Thanks. Let me end this class. Of course, if you have questions later, you can mail me or you can write in the Teams, whatever. Okay. Okay then. Thanks everyone. And I guess you have seen the announcement that there will be no live lab session today, but make sure that you stick to the deadlines about the assignments.